fluid mechanics is in rather dark gray, because I will be giving examples from fluid mechanics, but that's not the main thing of my talk. My main thing of my talk is about predicting and understanding, and I think we live in very exciting times where computing and data are coming together to help us do something which we have been trying to do for thousands of years. And before starting, I'd like to thank the organizers for putting this session together and for inviting me. I very much appreciate the opportunity. So I would like to tell you some things from my community. I come from the community of engineering, and I would like to tell you perhaps a personal history about computing and data interfaces, and I will do that by showing you a little bit about Bayesian inference, how data are entering the modeling process. And we have been speaking a lot about algorithms, we have been speaking a lot about models. I would like to stress that the way you use the data and the way the data are informing the models is perhaps a very, very important issue that many people perhaps need to pay more attention to it. I would like to tell you afterwards how do we use machine learning ideas. In particular, I will be talking about recurrent neural networks and long short-term memory for predicting dynamical systems. And I would like to show you, I'll be discussing whether machine learning can actually predict chaotic systems. And finally, I would like to show you how deep reinforcement learning can be used to solve some very complex problems in fluid mechanics. And in particular, I would like to show you how deep reinforcement learning allowed us to do something that we had not been able to do before. And I would like to discuss what has been the issue there. So let me start by discussing Bayesian inference, data, and flow models again. And I would like to show you how data is something that has been largely overlooked. So let me show you an example of some of the things that we have been doing in my community. We're interested in a process that is called blood-borne metastasis. And what we are interested to study is we're interested to study the transport of tumor cells, circulating tumor cells, inside the vasculature. So this is an animation of the process. The blood vessels are attracted to the tumor. Then the tumors are able to enter into the blood vessels through the fenestrations. They are being transported in the bloodstream. And people are trying to detect the circulating tumor cells. It's a very tough process. It's 1 per billion. And people have been developing experiments. There is a particular device developed at Harvard by the group of Mehmet Toner, where he's using a concept called deterministic lateral displacement, where the idea is that you're using some fluid mechanics processes and you're able to separate the large particles from the smaller particles. Here you have red blood cells and a white blood cell. Deterministic lateral displacement allows you, by the way, the small particles and the large particles hitting the posts to separate themselves. So the way the people have been designing these things has been quite ad hoc. So we decided to collaborate with Mehmet and to try to do simulations for this process. So we have been trying to simulate red blood cells. There is also the plasma that you don't see here. You see animations of 200,000 red blood cells. The device is the same as been used in the experiment. We are spiking something that we call a circulating tumor cell. And then we are performing some very large-scale simulations. And I will tell you what is the method in a second. And then we try to see if the concept of deterministic lateral displacement is repeated. And after that, what we were hoping to do is to basically get rid of experiments and to provide a design tool for how to design these devices. Here's a little homage to the fantastic voyage. You see how the circulating tumor cell has been followed. And then again, you spike this over here. And again, because the larger particles, they keep bumping onto the post, they keep being pushed out. And eventually, this thing separates. We got times that they were similar to what people will get experimentally. So we were actually competing at that time for something called the Gordon Bell. It was one of the finalists in 2015. These simulations are running on 1 million cores on Titan at the time. And talking about data, so these are, we were able to do, this is one of the biggest simulations on Earth actually in terms of size. This is about 10 trillion particles, dissipative particle dynamic particles for 10 million steps. And then I think we're starting to compete with Facebook size of data. One of our runs is about 3 exabytes of data. And of course, we are not alone. There is a lot of scientists in the community where I come from, in engineering, fluid mechanics. Yes?
What does that mean? Do you have to write that data, or was it
3 exabytes of data would be if I dump every time step into outside, which I don't do, right? But at the same time, why should the Facebook people collect everybody who has a hat on his head, right? So I mean, I will come back to that, and it's an important point that, you know, I can dump all this data, but what's the point? And I will try to tell you actually that it would be wrong to dump all this data, because probably lots of this data is useless. But sizes are there, and again, it's 1.4 billion things, 10 trillion particles, and so on. And the technology behind is quite exciting. So we said, let's do now, forget experiments. So I asked Mehmet to give me another device and to try to predict now what's going to happen to the red blood cell. Mehmet did that. He gave me the device. He didn't give me the flow. And then I put a question mark here because we failed. So where we failed is that the blood cells in the new device were actually doing something that they don't do in the experiments. And perhaps what you may not see here is that the red blood cells here, they are hugging the posts of the microfluidic device. And here we were finding that the red blood cells, they had a lot larger momentum than they should have. So we tried to find out why. And then just to give you what is this simulation technique, this is how you describe the fluid. You have all these gazillions of particles that are representing the fluid. And you didn't see these blue particles. You saw only these red blood cells. But you have to imagine for each one of these red blood cells that we model, there is all these dissipative particle dynamics particles. It's basically Newton's method, where you specify force fields between all these different particles to model different things. And of course, whenever you have all these force field models, you have springs and beads, and you have parameters. So you have a lot of parameters, and the question is, how do you choose these particular parameters? So when we do that, we have to do a process called validation. So I was collaborating with a colleague who has done a lot of validation, apparently. So he has taken a red blood cell, and he puts magnetic beads, and he takes the red blood cell, and he stretches it, and he does it in the computer, and then he finds experiments and simulations are agreeing. He has done another thing where he puts a red blood cell to go through a constriction, and the red blood cell is going through, and you can find very good agreement with the velocity. He has done all these different validations. He showed me all these different validations, agreement between experiments and simulations. And the question to you is the method validated? So I thought actually my answer is that the method is obviously validated. Do you agree?
Sounds like a trick question.
It is a trick question because I was tricked myself.
No, but tell us why.
It's no, because for every one of the simulations you change the parameters. So there is no transferability between parameters. And I'm afraid this is a trick that a lot of people do in computational sciences. A lot of people are choosing the parameters in order to match particular data. And whenever you see data that are something like a straight line, obviously if I have 10 parameters, I can probably find some tweak of the parameters so that I can recover this. So back to your question, indeed, it would be a waste to dump 1 exabyte of data, and every time I change the parameter, I will dump another exabyte of data. The big story here, which is also a lesson for high-performance computing, sometimes when you do high-performance computing, you discount the modeling approach. So the key thing here was that the viscosity of the fluid inside and outside the red blood cell is a factor of 5. The truth is that it's a factor of 5. We were doing it a factor of 1 because we didn't want to have different particles inside and outside, because if you have 1.4 billion cells and you have to go and do all the checks, your code is not going to be performing at 98% weak and strong scaling, but would be much, much less. So all these things going for the Gordon Bell made us to discount the model, and we should have had the viscosity ratio of 5 that we did not have. And I didn't pay attention, and sometimes the viscosity ratio of 1 gives you results, gives you valid results. But the viscosity ratio of 5 was important because when these guys were coming around, they didn't have the right momentum, and they were not heavy enough to stay and lose friction and stay around the posts. So this was the lesson about that. I'm sorry. This another, it's very low. It's a microfluidic device. It's 1 or so. It's actually no, sorry. It's high. It's high throughput. They push the blood very fast because they want to check a lot of samples. So it's about Reynolds number of 50 or even 100 for these things. The speeds are very high. Yes.
Is there some reason they don't do like a holdout experiment?
What is a holdout?
Like to only tweak the knobs on part of the data and then see how well it fits on the ones you didn't use to tweak the knobs?
Which knobs you mean? You mean about the numerical method? Yeah, sorry. Yeah, you can always tweak the parameters.
This in machine learning, this is like just known as overfitting, and there are principles.
But how do you know which one of the parameters to use for whichever case? So if I have, these are all different parameters, right? So here there is one parameter, the persistent length, that here goes 10 to the minus 9, here's 10 to the minus 7. There's the viscosity ratio. Here it's 1, here it is 5. This is 10 to the minus 6, same as this one, here and here. They are not. The thing is that what you validate, that's my message with these slides, is what you validate upon has to have relevance with what you're about to predict. And for this, you need data and you need physics. And you cannot do it by an algorithm alone. An algorithm alone will not do that. Yes?
So you're basically saying you overfit it to a specific experimental
Yes.
situation,
Yeah.
and it was not generalizing
That's
to a
right.
new experiment.
That's right. There's no transferability.
So they could actually validate it for this particular experiment, but the predictive power of the feature of the
Yeah.
parameter was 0.
Yeah. And the other thing is when you fit, that's a philosophical thing, when you fit to reproduce the data, what is it that you understand? Especially when there's no transferability. If there's transferability, you have an underlying theory about your particular parameters, and then this is some kind of truth behind that is transferable. But here it's not. So I'm afraid this is not the only domain. There's another domain called molecular dynamics. If you look it up, you will find maybe more than 100 million references, and I'm afraid many of them may be wrong, and I would like to argue why. So, so this is another thing that created a lot of commotion. This is flow of water inside carbon nanotubes. There was a lot of commotion because people said if the water that's flowing in the nanoscale, it flows by orders of magnitude faster than if you have water in larger pipes. And then people started thinking about desalination, etc. So if you do classical fluid mechanics, if you give me the pressure difference across a pipe, the length of the pipe, the viscosity of the fluid, and the diameter, there is a very simple formula. It's called the Hagen-Poiseuille flow that tells you the flow rate. Now, what people were observing experimentally and in simulations with molecular dynamics is this enhancement ratio that I will be talking about afterwards. So there come two very spectacular experiments in nature and science that said if you take a pipe and you shrink it to the nanoscale, then the flow rates that you get are up to 5 orders of magnitude bigger than if this is continuum. This is a spectacular result. And then first came the 2005 paper, important to remember this, and then came the 2006 paper from a group in Berkeley. I obviously found this fascinating, and I started to collaborate with these people. And then I started doing my simulations on nanotubes that they had an entrance and an exit, but they were short because I could not afford to do 2 micrometer nanotubes. You have to imagine that you're doing a simulation with an aspect ratio of 1,000, full of water molecules with electrostatics and everything. A lot of computing hours went into that. Now, the interesting thing is that if you draw a straight line, if you do some machine learning, then you find out that if you were doing a bigger length, you would recover the experimental data, and the world is in order, and the physics behind is that the length was not sufficient. Therefore, you have to do bigger and bigger simulations. But now, in fluid mechanics, we know that if we do a flow which is in a periodic pipe, a periodic thing is the equivalent of an infinite, and indeed ourselves and others, not only us, that's why the curve is so wide here, did periodic simulations in nanotubes, and they found orders of magnitude. It's not 10%, 50%, not a factor of 2, but there's 2 to 4 orders of magnitude difference between simulations and experiments. So who do you believe, given the previous discussion? So what happened is then with more sacrifices and thanks to the computing resources we have in Switzerland, we actually did these heroic simulations, and then there is uncertainty because I will explain why. But we did the same thing as the experiment, but we still found that there is this discrepancy, and we start to get more security because this matches the computational, the periodic results. And the interesting thing is that the people who did the experiments, new experiments start to come out later after our work, and even the people who did the results up here, they redo the experiments, and now they find results that they match the simulations. And it starts to be an interesting story. In fact, they said they had found these results, but they were afraid to publish them because they were ordering by 3 orders of magnitude before, and after the simulation results appeared, then they were comfortable to publish them. So as you understand, as we pursue knowledge, the knowledge that we pursue is quite imperfect. And in everything we do, there is errors, and it's actually fascinating that we're even able to ever produce anything out of all these mistakes that are appearing, not only experimentally, but modeling, numerical errors, and everything. And what I would like to say is that this imperfect path to knowledge is not hopeless, because there is, thank God, this 400-year-old theory of Bayes and Laplace and others, where you try to actually take into account whatever data you have, and then you try to create probability of models in terms of data and try to argue in this probabilistic fashion. What did I do here? Upsla, sorry. Yes, so now this Bayesian uncertainty quantification is quite interesting, because out of this very simple formula, those of you who have bothered, and I think there are many of you who have bothered, would realize that there is a lot of things that need to be done. How do you select priors? How do you do high dimensional integrals? And then what happens when your model is stochastic itself? And then what if you have unidentifiable parameters? So I would like to show you how this thing plays out in molecular dynamics, and I would like to show you uncertainty in water graphite systems, because this is what we were studying. This is graphene, or you can use this to make a carbon nanotube. This is water. You can have a water model that looks like that. There is other water models that look like that. I think Yulia Zavadlav will talk in the afternoon about coarse-grained models and their uncertainties. And the classical thing that people do is they say that these particles, one of the ways they interact with something called an NR-Jones that is inversely proportional to the distances. There is a power of 12 for the repulsion, a power 6 for the attraction. Where does the number 12 come from is a mystery. And then how do people calibrate? One way they calibrate is they take a water droplet, they put it on graphene, and then they measure the contact angle, and that's how you try to calibrate. But measurements have uncertainties. So Bayesian theory gives you a nice way to take all these different uncertainties and put them inside the model, and then make predictions using uncertainties. So let me show you how this thing helps you to study models. And the way this helps you to study models, let's look at this Lennard-Jones potential that I told you. You see here 2 parameters. One is this epsilon, and I chose to show you a computational parameter, which is the cutoff. Apparently, the bigger the cutoff, the more accurate you are, right? And you are doing 1 over r to the 6, 1 over r to the 12th, and then some people come and say, you know, instead of computing this 1 over r to the 6 by putting r to go to infinity, cut it off. And the classical thing is that the bigger the cutoff, or often they say that the bigger the cutoff, the better. But the results, when you do uncertainty quantification, and I will show you some methods afterwards for that, is you're creating joint probability distributions of these parameters. This is the cutoff parameter, this is the epsilon parameter, and you see this based on the data. The data we collected was data on the water contact angle. You have to remember that. So then we get this data, and then we take these probabilities, we marginalize them for one parameter or for the other, and the interesting thing that you see on the R-cut is that the maximum appears for smaller and smaller values, which to me says that the less you're using the model, the better off you are to predict the data. And that's actually what you find out. And I think this uncertainty quantification, we have applied it to this. And And actually, we have used different experiments to do the calibration. And indeed, we find that there is some consistency, that the computational results that I told you earlier are OK. And in fact, if you use this data to predict the opposite, you find unidentifiable parameters. So this discussion between data and models becomes very interesting.
Explain that statement a bit better. You said the more you use the more, you went very fast. Interesting statement that I did not.
Yeah, so you have a model. This is your model of how two particles interact, okay? And then this function should go to infinity. It's 1 over r to the 6, okay, to the 12. But then you say, I'm not going to do this for particles that are very far away from me. I'm going to restrict it only to particles that are close to me. And obviously, the less you use it, the less you trust the function 1 over r over 6 and 1 over r to the 12 that you said, right? So that's what comes out of the data. What comes out of the data is that the maximum place for the marginalized probability distribution is for lower values, not for higher values. You would have expected that this thing will go like that. On the contrary, it goes like that. So this tells you that you should use it only very locally for some reason. And as you go further away, this is not the right model to use. That's the, yes?
So polynomial decay is not good enough. So
Oh, no, it's the Lennard-Jones is what everybody uses. All we did is we accept the Lennard-Jones, and we accept the 6 and 12. We also we can change that actually now. We actually use neural nets now to do all that. But let's say we'll go back and look at what people have been doing molecular dynamics the last 30, 40 years. We take that, and then I can show you parameters of any type in molecular dynamics. I just chose these two here. And I'm just saying that the computational parameter of restricting the cutoff, the smaller you make the value, the better it is to predict, to match these results.
So basically you are saying cutting off Lennard-Jones helps you.
Yeah, yeah.
But I mean, the epsilon has a physical meaning, right?
Yeah.
That you don't really fit. Or you also
I fit also the epsilon. This is the values of my epsilon, and I find an epsilon which is down
you
here.
get that also from some other studies.
Of course you can get it from some other study, yes.
So in principle you know what the epsilon should be.
Here I pretend I don't. Okay, yeah.
And the 1 over 6 out to the 6, I mean that is true for neutral molecules.
Yeah, yeah.
But water has a dipole moment, right?
Yeah, I kept all the other parameters of the model constant. I have electrostatics, I have the angles, I have vibrating modes, I have all that, and then I allow, just to show you, instead of, just to show you, I just take 2 parameters and let's say, let me vary these 2 parameters, see what happens to my results. That's what I'm doing here. But you can tell me any 2 parameters that you have of interest, and I can run my Bayesian uncertainty quantification, and I can do that. In fact, if you follow Julia's talk this afternoon, actually I will come to the water in my next slide, because the water is interesting, because it's everywhere. So the other thing is, now again, I insisted on the data. So now I use some data on the water contact angle. So now let's say I have to use some other data. I forget carbon, forget everything. Let's say I'm doing argon. Argon is the most boring molecule you can ever imagine, but the viscosity of argon is changing as the temperature changes. So this is how the viscosity changes, and then these are different experiments and different temperatures measuring argon viscosity. Of course, there should have been here error bars, but for the moment, please accept this, and this is data, okay? Now, you have to understand that for every one of the experiments, there's different labs, there's different conditions. If you do pharmacokinetics, there's different patients, different doses, because this is a general problem. It's not only for molecular dynamics. So here's what happens if you take each one of these experiments and use it to calibrate now the epsilon and the sigma in my molecular dynamics. This is the probability distributions that I get. So you will get very distinct values. So it says here that if I take experiment number 8, which is the green things, and if I take, let's say, experiment number 1, which is the black things, my values would be rather different. Okay, what should be my epsilon and sigma? And one actually does not almost contain the other. So they're very, very separate. So how do you take into account all these different things? So Bayesian inference, the way you play with the data is important. So you can take all the data and cluster them, or you can take the data and acknowledge them separately. And the thing that we are pursuing more recently is the so-called hierarchical Bayesian methods, where you're assuming that the parameters of your Bayesian inference, they're having hyperparameters themselves. And that's a nice way to allow for shrinkage from different sources of the data, assuming that they're measuring the same quantity. The problem with that is that actually it becomes very, very expensive, because you double or triple the number of parameters you integrate. But the interesting thing is that when you compare classical Bayesian, the Bayesian inference gives you a way of comparing different models by computing the evidence, data-driven evidence. So for certain data, Bayesian inference, the denominator of the Bayesian inference, tells you which one of the two models is better. So if you take all the data and you cluster them together, you get an evidence which is this. And if you take the hierarchical way, you get an evidence of this. This difference of 3, you have to take it to a fact 10 to the 3. So it's about 1,000 times better to do the hierarchical way. Now, if you wanna calibrate the water, you have data about the diffusion coefficient of the water, the density of the water, and the radial distribution function of the water. You can play with different models, but the interesting thing is, let's say you pick a model, and then you calibrate. I don't remember what are the different values. I think the data down here is the radial distribution function. Yes, the data down here is the radial distribution function. The data up here is the density. The data up here is the diffusion. And this plot here puts all the data together, and this gives you the probability density for doing uncertainty quantification on the charge that you put on the molecule and on the epsilon. Yes?
You were talking about the normalizing constant or the marginal likelihood before, and you said it's better with a hierarchical model. Is this on data that's not been used?
The evidence.
So is that the evidence on data that was not used?
No, on all the data. If I take all the data on the viscosity of the argon and I process them in a hierarchical fashion according to each one of the sets,
You have more parameters. The evidence
I have the same amount of parameters.
number of free parameters.
It's the same number of free parameters, yeah. So it's a fair. It's the only way, the only thing that is different is, do I do classical or hierarchical? And I just argue that hierarchical is better because it makes sense that it is better.
If it's hierarchical, it seems like you reproduce sets of parameters for each sub-hierarchy, right? So how you integrate them out?
No, you have hyperparameters from which you get the parameters that correspond to each one of your data points. We can talk, I think it's especially in biology and in other fields where you measure, different labs measure the same thing, or people do MRIs in different hospitals. I think this hierarchical modeling is very powerful. We are not the first who do hierarchical modeling. Maybe we are the first who do it for molecular dynamics. This I believe. But you see the problem. You have the values from over here if you want to calibrate for diffusion, to somewhere in here if you want to calibrate for the radial distribution function. So that's for people like yourself who do molecular simulations. To me, this is concerning. Yeah.
So do I understand it correctly? This epsilon has a physical meaning.
It's the binding. It's the It's the affinity between water here.
So however, you now use it as a fit parameter because there are other physical phenomena which you are not taking into account. And when you then adapt this parameter, you get a better.
I don't adapt the parameter. I do uncertainty quantification for this parameter.
So when it's black, it's the highest probability for this particular epsilon.
For this data, for the radial distribution data.
Okay, for the data, to explain the data, you need that epsilon value.
To be over here. To epsilon and q to be over here.
That's what I mean. You have a different value for this epsilon.
For each data.
Depending on the physical situation.
Yes.
Because there are unmodeled model
Yes.
components which
Yes.
then can effectively take
Yes.
into account.
Yes.
Okay.
Yes. Same question or?
Yeah, basically, that is what I wanted to say before. It seems that you have several parameters and you choose some parameters completely wrong.
I don't
You try
choose
to
them.
Correct that, or you could try to correct that with an artificial epsilon.
No. Completely wrong impression. I'm sorry to say. You come to me with your favorite model. You have tested it. You have done anything you want. You present me with your model, And now I say, okay, very good, this is your model of water. And now I go to an experimental colleague and I tell him, please give me the density of water. Okay, you two are separate, I'm in the middle. Another one gives me the radial distribution function of water. And then I come back to you and I tell you, if you want to capture the radial distribution function, your values for epsilon should be over here. If you want to capture the diffusion coefficient, your values of epsilon and sigma should be over here.
But you have other parameters as well, right? The hyperparameters.
I can, yeah, but if I go into this higher dimension, the situation is going to look worse, because here I have used only 3. And the more parameters that I allow to vary, the more you will get the Kershaw dimensionality is going to come and hurt you even more than spreading things left and right. You will find a lot of different things appearing.
Okay, so we have to talk about, because I don't understand. I mean, we're doing first principle calculations, so we don't have really parameters in that sense. And we don't have really this, we don't see this arbitrariness which you see.
So if you do density,
I somewhat feel that you have some other condition.
It's molecular dynamics here.
Yes, I know.
So if you do density functional theory, which is a little bit better, it's much better, I can show you uncertainty quantification on the dispersion functionals for density functional theory. They can be all over the place depending on the data you use to calibrate.
The dispersion functionals is a severe approximation.
Yeah, yeah. Another thing, since you bring up the quantum mechanics, is if you give me, let's say we do an experiment and I try to do it with molecular dynamics, which is a middle class model, and then you do a full perfect quantum mechanics simulation on, let's say, 1,000 molecules, okay? You give me the data about the radial distribution function, and then I can take my model and I can calibrate my model to more or less get what you do. I can do uncertainty. Now someone else comes and gives me experimental data. I will get very different parameters. And we tested that, and we find that quantum mechanics calculations and experiments don't necessarily give the same parameters for molecular dynamics, which is a very concerning thing. And the most interesting thing is that the parameters that you calibrate with quantum, they don't generalize. They generalize worse than parameters done with experiments. So it's an amazing can of worms that has appeared, and I'll be happy to talk with experts like yourself. Or how do you put this in a proper way? But I think you need to revisit everything we have done in molecular simulations. So again, this is hierarchical and classical ways. How do you take the data and you put them together? This is the hierarchical, gives you very much broader things because it tries to sync all different domains. Here you see, for example, how these two different models, Mahoney and Jorgensen, and I don't remember what, Enrique et al. Here, this is the values they tell you to use. And when you do hierarchical, these are the values that you use. So, and if you do the classical, these are the values you use. So everybody has his model and publishes papers, but when you start talking with the data, you start to have another picture. By the way, this is TMCMC. I'm not going to go into that. It's all these things are very expensive. As you know, molecular dynamic simulations take a lot of time. We have to do thousands of them. So there's two things that we do. We try to do this thing called TMCMC, which is not from us. It's from Ching and Chen in a very strange domain that no biologist would ever read. But it's actually a way of having many parallel chains and to show actually that these parallel chains are helpful. And if you have a large parallel machine, you can do things with that.
Is that what you used for the experiments you just showed?
Yes, I'm using TMCMC, and then there is a variation of TMCMC we call XTMCMC. And at the end of, or somewhere in my talk, I will give you a link to this, which is a software. We call it Corally, because of all these different microorganisms, the different codes that live there. And you're welcome to download. There's CMA in there. And actually, TMCMC is the variation of CMA for getting the full probability distribution. CMA is like TMCMC by giving you the maximum likelihood. So there's a lot of beautiful things. And you can have all these things. We ask that you cite us if you use them. And we are not a commercial company, so we cannot offer support. But all these techniques, I think, so they do, we do take advantage of thousands of cores to do all these runs, because these are super expensive. These are super expensive. Now, I want to, So I would like to conclude here by saying that, yes, we have models, yes, we have algorithms to sample spaces, etc., but I think it's a very, very important to put data as a key citizen in this whole process, and to discuss with people who produce the data, and to use the data as a key part of the modeling. It can no longer be that we do things separately from the models. Now, the next thing I want to do is, okay, this is what Bayesian inference does. The next thing I wanted to do is actually this. So I want to tell you machine learning now for dynamical systems. And I would like to go back here. No, I stay here. and this is something on machine learning that I did in fluid dynamics back in 1999 when I was a postdoc at Stanford, at Center for Terminals Research. And I was almost expelled for doing this back then, because people wanted me to do large eddy simulation models, and I was doing machine learning, and I was very proud to take courses actually from Rumelhart of the backpropagation algorithm in the School of Psychology. So what was it that I was doing, so that you understand? I realized that the machine learning community has some beautiful ideas. One of these ideas is something called a linear autoencoder. Okay, this is the most trivial machine learning thing. You have some data as input, some data as output. You put a layer in between that has less size, and then when you train this layer with the classical backpropagation or whatever you want, and the activation is linear, like the simplest of the simplest, then it gives you the PCA. Now, if you look at the fluid mechanics community, how many of you have heard of something called the proper orthogonal decomposition? Okay, so if you go to Google, 400,000 results is basically a linear autoencoder. The proper orthogonal decomposition is that Holmes and Limley made a career out of taking the PCA, and the linear autoencoders are calling them POD. So how good is it? So how good is it? I'll show you. Here is a flow that you have a turbulent flow. And to appreciate what is this turbulent channel flow, this is, again, every snapshot here is about 32 terabytes. So I can do a lot of exabytes of data, but we don't dump them all. What you see here is the velocity field above the wall. This is the depth of the channel, and you see the streamwise velocity. For you to understand what is it that you see here is when you take your plane, and your plane starts to accelerate, this is the velocity field in about 1 millimeter cube. And for about less than a second, that's what happens over the surface of the plane. Okay, so we can go in there and study it and look at all the shear and all these different structures of turbulence, but then we cannot afford to dump everything out, so we want to do dimensionality reduction. So this is where actually I used this idea of linear autoencoders, and then it was very natural that you go and you put things in between and you make them nonlinear. So if these are some vertical structures, or velocity, whatever you want to call it, if this is the original, these are two original fields, this is what POD compression will give you for the same number of terms, and this is what a neural network will give you. So, and again, even when you show to people that machine learning is much more important than anything they were doing them, it took them about 20 years. On Tuesday I was to Stanford to celebrate actually this picture. Because back then nobody paid attention. Now everybody in Stanford is doing neural networks and machine learning for turbulence, and I was very happy to see this finally happening. But is neural nets the answer? I will show you. Actually, there's a lot of papers that they try to do these neural nets. One thing I didn't like is that you would get stuck in local minima. You didn't know when your training was done. But let's look at recurrent neural nets that all of you know. It's about time series. You have an input that is a time series. You have an output that is a time series. You don't want to do the all-to-all neural network because the input from xt will affect the output from time 1. But you want to respect this history, and this is what the recurrent neural nets do. And you all know that they have a problem with their training, and there's long short-term memory networks with Jürgen Schmidhuber. I met Jürgen Schmidhuber in 1997. That's when I moved to Switzerland. And when he showed me this, my training comes from numerical mathematics. This was so ad hoc that I didn't even want to touch it. Nevertheless, we wrote a proposal with Jürgen, and we barely got one student from the Swiss National Science Foundation. I think I'm thinking of submitting the same proposal, actually, see what I get this today, probably more. But it's about 21 years back then. But nevertheless, you all know the LSTM, that it regularizes recurrent neural nets. So we wanted to use it to see if we can do reduced order modeling. And the idea is the following. You're giving me a dynamical system, and I want to collect the data of the dynamical system to predict basically the equations without having the equations. A very interesting theorem that I like, which perhaps not many people are familiar, is Takens theorem, which actually justifies why recurrent neural nets are good. Takens theorem says that if you have a dynamical system, you can predict the attractor of the dynamical system by taking only one of the variables. Let's say you have 3 variables and you get this butterfly attractor. Instead, you can take only one of the variables and use the time delays of this variable to reconstruct the attractor. And you can see why time delays are important, because all the interactions that have happened between the other variables, they should manifest themselves inside the delayed signal. So if you have 3 parameters, you observe only one, but you observe it over time. You reconstruct the phase diagram of that one, and then that Takens theorem shows that it's equivalent to doing the full thing. Now, does this work? So we take a partial differential equation. This is the Kuramoto-Shivasinski equation. And if you take this equation and you reduce this nu, you reduce this number here, you make the equation to produce finer and finer scales. So this is the scales. This is x and t. It's a 1D equation, and this is the contours of u. So this is 1/10, 1/16, 1/36. You start to get all these different structures. We discretize it with a numerical method. And these are, if I do POD modes, this is the number of modes that I use, about 20, and I capture about 90% of my energy. So does this work? So now what is it that we do? So we try to use recurrent neural nets to do the training. And I will tell you up front that using recurrent neural nets on the complete signal did not work. Pantelis, who is back there, is suffered through all that and is the person who did this. So instead, what we decided to do is to take the signal and to do an SVD of the signal. So if this is the full PDE and this is the SVD, this is how the two things are evolving. So this is how the full signal is evolving, and this is with, I don't remember how much, 97% of the total energy the modes would evolve. So now we use this as data to train the recurrent neural nets. I want you to pay attention, because it's an important issue. It avoids a lot of noise that is introduced by this. So we take that, and then how good is this? How good is this? I will show you how good it is here. So this is the time 0 that we have the LSTM. So you have two things. You have now the dynamical system on one hand producing data, the green things, and you have now the recurrent neural net that has been trained for a little bit, has been trained on this data. Okay, so you do this on the SVD data, and then the recurrent neural net is dumping afterwards output, and this is how it compares. It keeps up with the dynamical system for a while. It keeps up for a while, so up to 0.8, up to here. So he has been trained down here, and up to here he keeps reproducing the results. Okay, and then it's going to fail. And then, so if we look at the error, this is how the error goes over time. So you see at the beginning you have very little error, and then after a while you start to lose it. But this is the best we could do, because as soon as you actually, as I told you, there is a parameter of the equation that decides the smoothness. So if the parameter is 1/10, the solution is quite smooth, and this thing is working. But as soon as you make the parameter 1/16, recurrent neural nets, at least our implementation, fails miserably. So it cannot produce anything as the system becomes more and more chaotic. Okay, so that's a lesson that we learned. Now, what we did after that is to add stochasticity. So we combine LSTM and something called mean stochasticity, that you take the data and you try to look at the statistics of the data. and together with a recurrent neural net, you are giving them as input the stochasticity of the system. It looks better, but it doesn't blow up. But still, the accuracy is not there. But so that's the other thing. Finally, one thing I want to say also is that this paper appeared in Wired and other magazines, and this is by a group. The group which behind that is the group of Ott, Professor Ott in Maryland. I don't know if people know him, who does something called echo-state networks. Okay, and then Professor Ott's group said, we predict chaos using echo-state networks, and then we looked at it. We looked at this article, and actually we found surprising that this article actually mentions our work, and it says also the group from ETH also confirms the work of Ott. But we did not. We actually say that it does not. And in fact, what Ott was doing, there is the different Lorentz systems. So there is Lorentz 96, there is Lorentz 63, there is Lorentz anything you like. So what Ott and we can do also is we can get the simple Lorentz systems. Lorentz 63 we can get. Lorentz 69 nobody gets. So machine learning has no ability to predict chaos to the best of my knowledge, but this would be a great place for machine learning people with techniques that are better than what perhaps we know to enter. But there is something else we can do. So it's not one thing or the other. Okay? It should not be either physics or machine learning. There is some fantastic room in the middle, and that is the next thing that I want to show you. And the next thing I want to show you is what if I have some reduced order model, and then I help my reduced order model with data. Is this good? So you see, I don't go only POD or only, before I would go only data. Forget about this. But now I'm trying to help my data with a reduced order model that I have constructed, and actually this is actually turning out to be quite exciting. There's something called the Charny-Devore system. This is the phase space. These are, I don't remember, it has 5 variables. This is one of the variables. This is one of the dynamic modes of this variable to show you extreme events. And then if you do only model-based, if you do only POD, this is the phase space that you get. If you do the new method that we do, and this is work with Themi Sapsis from MIT, that we do POD plus data, we do a very, very good reconstruction of this thing. So very quickly, I want to say a summary between machine learning and Bayesian inference. I think someone mentioned yesterday that these are one and the same. They're not. And I think there is a lot of things that can go in between. So machine learning is actually relatively inexpensive. I think many of the colleagues here mentioned how nasty this thing is. And you have to appreciate there's a lot of tools and effort that has gone to make this as useful with the machines that we have today. But still, it's expensive. But at the same time, I like very much this Bayesian inference because it gives you distribution of parameters. It can quantify uncertainty. You do get the prior knowledge. And these are some of the things that classical machine learning does not work. But I liked very much what you call this oracle, because machine learning actually can be used as surrogates to, instead of doing the large-scale simulations that we do here, we can use a neural net, what you call an oracle. Instead of running a full molecular dynamic simulation, I run my oracle and I help. And then we do a lot of work where we combine these two things all the time. I'd like to close with something which is a success, in my opinion, of learning, and this is deep reinforcement learning. And where we used it is for a question that I had since childhood. I grew up in a fishing village. I was always watching these fish, and one question these people ask is, why do they do this? Why do they do that? Is it an energetical benefit, or they want to stay close to their friends? So in order to understand this, you can go and watch them. This is my video with my iPhone in my village again. And you can watch them and try to understand. But what we did is we said, let's try to put these things together to find out if I can take two fish and put them to swim together, then I can understand what's going on. There is a lot of engineering applications. And there is a lot of interesting, one spectacular application is this. People are putting wind farms like that, and I will show you in a second they should not be doing that, because when the wind blows from here, all this area is dead. And there's theories that people came up and then they said fish maintain a formation, but how do fish maintain a formation? You never see fish maintain formation except here, where fish actually do maintain a formation. And can you tell, do you know what has happened here? People know this video? These are real fish. So the fish, the fish have eaten food that contains magnets, and then there is someone under the tank with very strong magnets pushing the fish. The guy had lots of trouble, I think, from various animal organizations. So if you take two fish now, and they are self-propelled, and you put them one behind the other, a fish that spends energy to move. The energy is in this rotation. This is the vorticity. This is the rotation of the fluid. Blue is like that, red is like that. So all this energy is in the fluid, and depending how this energy interacts with this guy can accelerate. But if you move this guy a little bit, it actually slows down. So you cannot, we tried to make it into an optimization problem to find out arrangements, but it didn't work. The only thing that worked was deep reinforcement learning. And the idea of deep reinforcement learning is to find out actions. For us, I will tell you in a second what are actions, and to find rewards, and to find states. And you have seen the success of deep reinforcement learning in many fields. I also have a personal story about the AlphaGo. If you know the authors of AlphaGo, one of them is Tore Greipel. Tore Greipel happened to be a postdoc in my lab about 20 years ago, 20 or so years ago. He's one of the smartest person I ever met, and he liked to do Go. He and Nicky Schraudolph wanted to do Go. And I kept telling him, please stop doing this Go and do fluid mechanics. And then they said, no, we want to do Go. So it didn't go very well, as you may understand. Tore left for a better place after that, and I continued in other things. So I'm really proud to have interacted with Tore. I'm not sure he can say the same thing about me, but at least the AlphaGo has been a success. So this is something I totally missed, because I just want to do reinforcement learning for fluids and not for Go. And Tore wanted to do it for Go, and I'm glad Tore did it for Go. Other things that reinforcement learning has done, and this is again a criticism. I'm afraid I will be eaten alive after this. Reinforcement learning has been used, to the best of my knowledge, only in games. There is not a single physics application that I have seen. So it has been used for all these different things. And this is all great, but the physics that are in here, I'm not going to make a judgment if they're bad or good. They're cheap. They're very fast to do. Okay? It takes you no time to do that. If you want to do a Navier-Stokes simulation like the ones we do, this take lots of hours. Every run could take about 6 hours in one node of pitch damped. So these things, in one node of pitch damped, you will do 100,000 runs. We do only one. So we had to do parallel computing if we want to do physics. So this is, so again, this is all games. And another thing that was very inspiring for me is, again, for fish, reinforcement learning has been used to do animations of schools by Dimitri Terzopoulos from UCLA. And if you look at the physics that Dimitri is using, that was actually another motivation for me. There are no Navier-Stokes equation. It's just some rules, ad hoc rules with no validation. They do look reasonable and everything, but it's not the real thing. So if people talk in reinforcement learning about this transferability of learning, I would be careful. So very quickly, we're doing Q-learning. We're doing Q-learning, and we are using recurrent neural nets with LSTM to do the approximation of the Q function, which is a sophisticated thing. And there is one more sophisticated thing that should be, all the credit goes to my student Guido Novati, that's similar to LSTM, that is using data from past, from the memory. He's trying to do the same thing for the experiences. For those of you who are knowing reinforcement learning, when you play the game many, many times, what are the experiences that you have that you try to use in order to decide your policy? So Guido came up with this beautiful idea that I will comment again later of this experience replay. So what is it that we get? Just to give you. So these are the states. So the states that we have now, it's a continuous space. So this is, so I have 1, 2, 3, 4, and 5 the current maneuver. And then this is all continuous variables. If I were to discretize them, and we used to discretize them before, you get very high dimensional spaces. And here is the reward. We tell a fish, we give it as a reward either to optimize its efficiency, swimming efficiency, or the distance from the front fish. And then the actions is to increase or decrease your curvature. So this is a comparison of two algorithms. This is trained fish. This fish and this fish, they try to stay on this line behind this fish. This fish in front does whatever he wants. These guys are autonomous, self-propelled, and after they have been optimized, they have to do this. If you do the classical lookup table reinforcement learning, you will see that this guy, sometimes he suffers, and his learning is not so proper, but the continuous deep reinforcement learning hits it right on. The one surprising result is if you try to look to optimize for efficiency, actually you find out that it's efficient to swim in the wake. These guys, they find places where they have to align themselves, and then they use the energy, and you have to see a very beautiful ballet with the way they're moving their head, respecting the rotation of the vortices. All these things, we could not do it without reinforcement learning. You can take, I have spent, at least myself and whoever else has looked into swimming, we could never solve this problem. But now we can do it. And the other thing we can do is you can have now autonomous things that the front fish decides to do whatever he wants, but then we tell this guy, please extract as much energy as you want, as possible. And indeed, the front fish does all sorts of maneuvers, and then we find out that the algorithm is robust to get it to work. I will not go into many details because we'll have to talk about flow physics, but I want to tell you that this also works beautifully in 3D, and this is a state-of-the-art simulations, because it's not very often that you see Navier-Stokes equations for two self-propelled animals and reinforcement learning here. Of course, you can ask the question, there is one more cycle that is being wasted here from the front, so you can have two guys behind harnessing it. And again, this is full-blown Navier-Stokes, which means if we were in an experiment and we were able to look at the vorticity, we should be able to see the same results, but we understand amazing physics that we were not able to understand before if we didn't have reinforcement learning. So I think this is very exciting. It was published in PNAS, but before it was published... What?
How do you assess that?
I have all the forces, I have all the information. So I have every pressure and shear on the body of the fish, and I can measure how much energy is being expended.
In simulation?
Yes, but the Navier-Stokes equations is the momentum equation for a fluid, and it's accepted that in the macro scale it describes fully the physics. It has a problem that it has this viscosity, but these are small fish, so there is something called the Reynolds number. So if the Reynolds number is 5,000, relatively small, I resolve every scale. So I am confident about my, so it's like I have a water tank, but it's in my computer. Just to give you an idea of what it takes to publish when you go between fields, this is when we try to submit a paper in a fluid mechanics journal. In one place in our paper, we said, and here is the celebrated Bellman equation. Those of you who do machine learning know what the Bellman equation is the equation of dynamic programming. And the guy said, the equation is described as celebrated, but I doubt that it's celebrated much in the fluid dynamics community. So this is this community. And then there is this other community that we show them that we can do fish and things like that. And complex physics says, yeah, but have you tried it on Atari? And then you can never win. I want to close by saying something else, that it's an elephant in the room that not many of us have talked. When we do all these things, we spend energy. And we spend a lot of energy to do fish swimming, and who cares about fish swimming? And we spend a lot of energy to do simulations of blood that are not really blood. And I think as scientists, we should be worried about these numbers. That every time we fire up one of these big supercomputers, It's equivalent of having 20,000 houses having electricity. There is more issues about computational literacy. People should learn to compute or be computed. And also, that's something I guess that the machine learning community also worries very much. But I think it should worry also the rest of the simulation and the computing community. I brought the example of molecular dynamics. I can give you similar things for any field of engineering. The trust is not only about AI as being advertised. Every field of computing has a problem, and we should be quite open about that. I want to thank you, and if there's time, I'm happy to answer any questions.